Alright, we're on episode 18 of our video series going from a noob to a veteran ASM coder. For today's episode, we are on the expert level thread of calling functions. Learning how to call basic static functions within the game using ASM. So what do I mean by function? So essentially, Mario Kart Wii, the developers that made the game, used a program, alright, and they wrote it all in C++. So then they put it into a compiler that would put it into machine code, aka PowerPC assembly, therefore Broadway could execute it. So when you're viewing the code view of Dolphin, you're actually viewing segments and little portions of all these C++ type functions. Now, anyone who knows about C or C++ will understand that it's basically a generic library of functions, things you may have heard of such as printf, memset, memcopy, square root, sine, cosine, stuff like that are included just by default in MKWe as well. So MKWe contains a lot of generic C libraries as well, and of course, being a Wii game, there's special functions, things for like the logging into the server authorization, and obviously we have the physics engine of MKWe, the static r.rel, which has all its own unique functions and whatnot. So that's what I mean when we say function. So when you want to really create complex codes, what I've been teaching for the past episodes is doing things in a dynamic sense, right? Or a dynamic analysis. While that can be good, what you're essentially doing is just you're editing little bit portions of these C++ functions, just the tiniest portions that you can imagine. But instead of editing these portions or whatever, we do things in a static, using static memory, a static analysis, if you will. And if we want something done, chances are the game has a function that can do it for us. You essentially provide the arguments for the function and you call it essentially and it executes it. So this can be done for codes if you need to do checksums, you need to create files, you need to shut down the operating system or the Wii, you need to restart the game. These types of cheat codes would never be possible in a dynamic sense, only in a static sense, by knowing these functions and whatnot and calling them with their right arguments. Top tier developers, really smart people over time, have created these things called symbol maps for the game. Talking about developers for the community, not the actual real developers of the game. So we were able to get these addresses for a lot of these functions, especially for all the generic C library functions. And so we have a basic, so this is the symbol map, and this one's for the main.dol, and as you can see, it's a lot. Most of these won't have arguments provided, but it's just still a really good reference. There's a lot of good stuff you could use here for. Unfortunately, on mkwe.com, we don't really have anything for the static r.rel. I've personally discovered some functions that I use in codes, like for my pal yourself at any time code. That's all done statically. I actually found functions in the static r.rel and I called them with the arguments. It wasn't like I was doing that manually. The functions that I was using to make the code possible already existed in the game's memory. So with all that being said, this is how you create really complex codes. Maybe down the road, if you get a thing called like Jydra, you can start your own symbol mapping, and maybe, who knows, we can actually expand on the symbol mapping on the physics engine, because we basically got everything for the main.dol. So with all that being said, let's talk about how you would even call a function to begin with. There's two options. You can either use the link register, or you can use what the register you figured out about in the previous episode, the CTR. So essentially you would take, if you would know the function's address, and keep in mind all these addresses vary per region, except for maybe a few of them, like the generic ones like memcopy and memset, the very generic C library functions. But for everything else, they will vary per region, and porting these addresses per se are extremely difficult. I'm not going to go into why, but it is very difficult. So even though we have the symbol map here, I went ahead and created my own thread in the hacking general discussion of ones I personally use or use multiple times, and I could go into great detail about arguments and other such details. So this one is OS shutdown to standby. This function will force the Wii to shut down to the red light mode regardless of how your Wii is configured. So even if you have like that WC24 feature where your Wii will shut down to yellow light, this will bypass it. So we will just use PAL for this example, since the symbol map, universally everyone who's worked in symbol mapping in MKWii, PAL is the standard. It's just the way it is. Some people hate it, some people like it, but that's what it is. So here we go. We got the address for the start of the PAL function. Most functions will start with something like this. I'll just put some X's here, but they'll usually start with some type of store word update instruction involving the stack pointer, aka register 1, and then it'll store various registers, whether they'll be general purpose registers or floating point registers, to the stack pointer. And functions usually end up with something like that. It'll have like a load multiple word or a load word regarding the stack pointer, and then it'll actually do something like this to bring back the old stack pointer, and then branch to link register. So when you see these three instructions or something similar, that lets you know you're at the end of a function. Okay, so we have our address for the shutdown to standby PAL function. So to call this function, to even set it up to call it, we can use something like this. You set the address, and you have two options. Either you can use the link register. So what this instruction does is it takes the value of R12 and move to link register. So keep in mind when you're doing this, whatever is in the link register beforehand gets wiped. And then you would do this. This would branch to the link register, aka it would jump to the address that's in the link register, which is here. And you'll be beginning of that function, and instructions will start executing there. Or you can use the CTR like this and branch to the CTR. So you got two options. Me personally, I like using the link register. I've noticed other people like to use the CTR. It doesn't really matter what you use, whichever one suits you. So another thing to talk about functions is some functions require a thing called arguments, some don't. So arguments, okay, we'll just put this here. We'll leave this here for now. We'll just erase it. Arguments start in R3 and go through R10, and they can go through F1 through F8, if I recall correctly. This might be wrong, this range right here, but it's F1 to something. I can't remember really. But either way, functions that have a lot of floating point arguments, like 5 or 6 of them, are extremely rare, even if they exist. So you never really need to worry about this range. You will have some functions such as sprintf where you might have to use F1 as an argument, but it's very rare. So really, when you're a beginner and you're calling functions, 99.9% of the functions, their arguments will have to be, there'll be some type of integer value or memory addresses. Thus, we would only need to be concerned with the GPRs, general purpose registers. So it goes like this. First argument, if applicable, goes to R3. Second argument goes to R5. Third argument goes to, second argument goes to R4, excuse me. Third argument goes to R5. Fourth argument goes to R6, etc., till R10. So if a function has 2 arguments, it would use R3 for the first one, R4 for the second one. An argument could be something like a mem address that points to something, or it could be something as an integer value and whatnot. It can vary. There can be other options, but basically that's what it really comes down to. Either some type of integer value to represent something, or some memory address to point to something. For the shutdown to standby function, it has no arguments. It doesn't need any. Once you execute it, the function knows, the game knows that you just want to shut down the Wii. So going back, let's say we're going to write our source. this would work. We don't need to be concerned with what's in R3, R4, R5, etc. It doesn't matter. No arguments. So if you turn this into a cheat code, this would shut down Dolphin as well too. This works on Dolphin. Some functions, obviously, they won't work on Dolphin. Like things like OS return the menu will only work in certain Dolphin versions just because Dolphin is Dolphin. So if you went ahead and made this code, and let's say you used a shared item code address, it would shut down Dolphin the moment you hit an item box. So with that being said, let's continue down. We talked about arguments. Relinking. This is important. Okay, so the issue is, let's see if I can find, here we go. We'll exit out of that. So this function right here. Okay, so for example, let's say you have a function like this. NetCalc CRC32 calculates a 32-bit checksum. Well, if you just went and called the function like this, move to link register R12, branch to link register, there would be an issue, because the reason why these shutdown functions work, because it's going to shut down the Wii anyway. It's the end. It's the end of the session, if you will. With this, if you branch the link register, there's nothing it can go back to. It essentially doesn't know where to go back once the execution of the function is over. Does that make sense? So when you're dealing with functions that are not meant to exit the game in any way, shape, or form, or to restart the game, they require a relink. So to relink, you simply do this. And this is branch to LR and link. That's what it means. So let's have this function right here. NetCalc for PAL. Okay. And so for NetCalc, we have two arguments, R3, R4. Okay, so what we would use, what would we calculate a checksum for? The game would use this function if it needs to create a checksum for an amount of data in memory. So R3 points to beginning, the beginning of where this portion of this data memory is at that you want the checksum. R4 is going to represent starting at that point, at R3's point, how much data in bytes are we going to checksum? Alright, so let's see. Let me run the PAL game really quick. And actually, we'll go back to this really quick. So just understand that we have these two arguments. Now, when we relink, a lot of functions have a return value. So once you call this function, okay, it will return a value. Usually only R3 is for this. Sometimes some very rare functions will have two return values, R3 then R4. If there are ever more, it just goes down the list, starting at R3 going down to R10. But for the NetCalc, R3 after relink, when the function gets over, R3 will contain our word value, our CRC checksum value that was calculated as a word value. So I know this seems pretty confusing, but I'll show you a visual representation in Dolphin how this actually works. So we'll go ahead and do that really quick. Let me boot the PAL game really quick, just so we can select a port of memory we can checksum. Here, we can checksum this. We can checksum like these random values right here. So we're going to go back and write our source. Let's get this back up. So we're going to have this source. We're going to use the shared item code address, okay? So what we're going to do is go set an instruction breakpoint on the shared item code address, so it will pause there, and then we can step by step this source so you can actually understand what's going on. So let's do that. First we're going to set the arguments. So we're going to use this right here. Okay. Let's just do this. LIS R3 80 51 ORI R3. Now pay attention. Notice we're setting the memory address that's pointing to the data that we want to checksum. We're going to checksum 2 rows of data, just 20 bytes in hex. So these 2 total rows from starting from this byte to this byte, it will checksum. So then we'll just put that there like this. 1D ORI R12 R12 0 times 1CA0. Move to link register. Branch to link register. Okay, so this will help us demonstrate. Let me just put that in a compiler. Make sure got 81D 1CAO. Make sure our function calling address is right. Okay, but let me put this into a C2. And what I'm going to do is we're going to get the shared item code address. For PAL. And that's what we're going to use for the breakpoint, because whenever you're making these functions and you want to test them, a little FYI, it's really good to use the shared item code address, because you just go in the game, set your instruction breakpoint, and then you can start a race and hit the box and know that the game is going to pause when you hit the box. So here we go, we got that. Alright, let's stop emulation, force stop. I wish this was default. Let's go ahead and apply this code we made. Add new code. Let's call it checksum. Okay. Save. We're good. Now we're going to copy this address right here. Launch the game. Set the instruction breakpoint to the static memory address. Let us rehook memory, Dolphin memory engine. Let's go ahead and hit a box. Give me a sip of water. And I know some of you guys might be confusing, like what, you have no idea what I'm talking about, but once we get to this code view, this will really show you how these calling the functions work. I'm also going to show you a tip how to do debug and analysis when we're doing function calls. Just going to wait for the there we go. Okay, so let's look at the code view. Now you guys should understand from that one earlier episode when we talked about basic debugging and analysis of ASM codes, why we have this branch right here instead of the default instruction. Obviously in the source we wrote, I didn't include the default instruction because it just doesn't matter for the purposes we're using. Okay, so now let's go back to the registers. Okay, so here we go. Let's start stepping through. Okay, so we're going to set our arguments for the NetCalc CRC checksum function. So obviously we have the memory address in R3. First argument is going to point right here, okay? Now step through 20 bytes in hex, 32 bytes in decimal, which is 2 rows. It's going to start at this byte and use all this data ending right here, and then it's going to calculate a checksum based on that data, okay? So now what we're going to do, we're just putting the NetCalc functions address, the address of the function itself, in the R12. That's how I usually do it. So now check this out. Look what happened to the link register to the right here. It's now in the NetCalc CRC function address. Now, excuse me. Now, remember what I talked about the earlier function OS shut down the standby? We just needed a branch to link register. We did not need a relink because the Wii's going to shut down anyway. We don't need to return back to where we started off before we called the function. It doesn't make any sense. Excuse me. Got a little burps. Okay, so I'm going to set a breakpoint here. Now in the basic debugging analysis thing, we talked about you can set instruction breakpoints just by left clicking to the left of an address and code view. Now, why are we doing this? Well, this makes sense, right? We want to check the return value of NetCalc, right? And remember I told you the return value is going to get an R3. So once this function returns back, there's going to be some registers change. The rest doesn't really matter. We just want to focus on what R3 is going to be, okay? So obviously, you wouldn't need to bother doing this type of breakpoint debugging and analysis for a function that you're just branched to link register without a relink. You only need to do this for relinks. So this is really good to make sure your function calls are right, because a lot of function calls, if an error occurred, this is really important to know, they'll return a signed negative number in R3, indicating that something went wrong with the function, whether there was a misalignment problem, you had an invalid register argument, or just something else crazy went wrong. Maybe there was an issue with memory or space or allocation or something like that. So this is why we're putting an instruction breakpoint right after our branch to link register and relink instruction. Now what you could do is you could press your hotkey to resume emulation, and instantly it's going to stop right there in a split second right here, and then you can just look at the return value. But just for sake of video, we're going to step into the function itself and let's see what it looks like. Now I told you most functions will start with a store word update messing with the stack pointer, aka most. This is one of those functions where it doesn't, okay? Now these are the instructions that the game is using right here to calculate the checksum, okay? And if we scroll down enough, notice here at the end we have a branch to link register, which will put us back where we left off. Now what I'm going to do is I removed my hotkey for resuming emulation from earlier. We can just go ahead and step through really quick and notice how instructions are executing for the checksum to be done. Now I'm going to resume emulation, and it's going to pause at that instruction breakpoint we set right after the relink. So the very moment this instruction gets completed, the game will pause. Okay, and it paused instantly. It's like super fast, you couldn't even tell. So look in R3. What do we have? Right here. So this guy, let's go back to our text editor. This is our word value, the game's CRC32 checksum value that it took based on these two rows of data. Isn't that pretty cool? And then what we'll go ahead and do is now we can just step and look, you're done with your ASM code, you're continuing back to normal. Okay, so now that we got that all out of the way, we need to cover a few more things with calling functions. We talked about return values, we talked about relinking, backing up registers, register safety. Okay, so obviously what sucks about calling functions is you can't do the plain Jane standard protocol for register safety. So we gotta follow a little different protocol, okay? So because we're using like stuff like R3 and R4 for arguments, we're getting return values in R3 and whatnot. So we have to push and pop the stack a different way. So those instructions are given to you in the thread, which you can use. As usual, we talked about in previous episodes, your default instruction could reside at the very top, or it could reside at the very bottom. You can see the pushing the stack instruction is a little different than the older one we talked about in previous episodes, but this will back up R3 through 31. Okay, so let's go ahead and just remove this comment. Alright, so there, that makes it a little bit easier. And then we restore the values and pop the stack. So the issue here is, depending on what you want to do with your code, you may have other registers you want to back up, right? Okay, so what happens if R0's value needs to be backed up? We got an issue, right? Or we need to back up the link register or something for whatever sakes. So it really just depends on the code. Sometimes you don't need to back up you either have to back up R0, link register, or CTR. It really depends. A lot of times you don't ever need to worry about backing up the CTR, but there'll be cases where you need to back up the link register, and a few cases where you need to back up R0. So if you need to back them up, you would use these instructions first, because remember we talked about R11 and 12 have that safety rating, so this can still apply here. Put R0's value in R11, put the link register value in R12, then push the stack. So these are all on the stack. You have your contents of your ASM, and then what you do afterwards is after you pop the stack, you retrieve LR and you retrieve R0's value and put them in their proper places where they were before your ASM code is even executed. So that is what you need to do if you need to back up R0 and or the link register. I don't think I've ever been in a situation where I had to back up the CTR, but that's self-explanatory. Just replace this with like CTR instead of LR. Easy to do. Some other things to note. If you're making a code calling multiple functions, like let's say you have the first function, whatever it is, it gives you a return value in R3 and that equals 9, okay? And then the second function you have to call, and then the third function you need to call. But in the third function, you need this 9 value for, like, let's say an R4 arg for whatever reason. Instead of doing a weird method, because you already push and pop the stack originally, right? So the original data for your ASM code for the game's already saved that you can retrieve at the very end. Instead of doing something silly like taking 9 and storing it to the exception vector, we can use registers R14 to R31. They're safe to use because remember we popped the entire stack. We pushed the entire stack earlier from those instructions I gave you earlier. These are called, I don't know if I've explained in previous episodes, they're called global variable registers. So with 31, this is how the game treats these registers, with 31 being the most important and 14 essentially being the least significant or the least important, essentially. Not going to go into great detail, but so after you call this function, this is what you would do. Let's go back up here, and let's say it's an R3. All you need is a simple move register. So if you haven't ever used this instruction, all this does is it copies the source register value and pastes it into the destination register. So copies R3 value, puts it in R31. So after this is executed, R31 equals 9. So let's say you do the second function, you do the relink, because this is all assuming you're doing relinks. Relink after this, relink after that. Now your third function comes. You need it for R4. So when it gets time for the instruction, you need that number 9 right here. You need it in R4. Boom. You just do this. And let's say you're at the end of your code. Well, you're all good because remember, right here, we're popping the stack and retrieving the original stack stuff. So the game can function as normal. So this is how you would use the global variable registers to back up values. You wouldn't need to do something silly like store them to the vector area or even something crazy like finding a function to allocate memory. That's not needed. So this little move register instruction can be very handy. For any codes that call a lot of functions, like a lot of codes you see I made editing NAND files and whatnot on mkwe.com, you'll see a lot of these move register instructions. And that's really about it, guys. That covers episode 18 for calling functions. Very necessary for making very complex MKW codes. Alright, and then in the next episode, number 19, we'll cover the final thread for expert level. C0 code types. Alright, that is it. Thanks for watching.